Welcome to the third part of introduction of filters. In part 1, as part of the introduction of filters, we looked at a terminology called impedance. So we defined impedance as a resistance to current flow. And we also saw how to combine different impedances in our electronic circuits. In our discussion in part 1, one combination of these impedances resulted in a unique type of filter called low-pass filter. And we have seen how it was possible to pass low frequency signals while damping high frequency signals. And in part 2, another combination of these impedances resulted in a high pass filter, and we were able to damp down or attenuate a low frequency signal and pass high frequency signal. In this lesson, we will see some more of these impedance combinations and the filter types they will result in. Now, let's look at another circuit. We are interested in voltage output across the resistor again. So how we analyze this is in the same way. Let's consider case 1. So case 1, let's consider what happens at low frequencies. At low frequency. So at low frequency, the effect of the inductor exercises that. So the inductor acts short circuit. Okay, but the capacitor, as we know, at low frequencies acts like an open circuit. So therefore the total effect is, if that's short circuit but we have an open circuit here, and the total effect, so we have open circuit, okay, as a whole, and voltage dissipation across this is going to be high. Okay, so there's no voltage to our resistor, so therefore our V naught over Vi is going to be 0, okay, almost 0. But this is the only effect we have is the inductor effect here. Now we'll see what it means. Let's consider case 2. Case 2 for high frequency, okay, frequency, and now this effect will be reversed, which means the inductor acts like an open circuit, but the capacitor acts like a short circuit. Okay, now so the total effect, it says that still that acts like an open circuit, yeah, but our capacitor at high frequency acts like a short circuit. But again, the total effect we have is an open circuit. So again, high voltage dissipation across these two elements, at the result no voltage, almost 0 voltage across our resistor. So again, V naught over V source approximately is again 0, but with the capacitor effect. So therefore, what does the output response looks like? At low frequencies, the output is 0, but as frequency increases, we will see the inductor effect. Okay, so it starts from 0, but our inductor effect, it says that it's a linear relationship, so it goes like that at low frequencies. But at high frequencies, then again the gain is going to approach 0, it will approach 0, but we have the capacitor effect, okay, so which is approach 0 but not a linear, rather it is a decaying exponential function like that. So as frequency increases, this will unfold to be something like this. And if we look at the equation for our gain, so we know that our output voltage is given by the voltage at the source multiplied by the impedance ratio, which is R over the total impedance. So R over R plus J omega L plus 1 over J omega C. This can be simplified as Vs times R over, so they multiply the denominator with these values. That will be J omega CR, and J times J will be minus 1 omega square LC minus J omega square LC and plus 1 over J omega C. So we can further simplify quickly as follows. So this is a denominator of a denominator, so we can multiply that with that numerator there. So you'll have J omega CR over now we'll simplify this denominator further, collecting real terms together and imaginary terms together. So 1 minus omega square LC, that's our real component, and in the imaginary component we have J omega CR plus J omega CR. Okay, that is, so therefore we have V naught over Vs. Okay, now let's see something interesting here. So we're driving this circuit at omega 1 over square root LC. Okay, so when omega is 1 over root LC, then if you insert 1 over root LC here, we'll have V naught over Vi, which is V source. So this equals J omega CR over 1 minus 1 over root LC squared. Okay, squared times LC. Okay, and of course plus J omega CR. So for this part we have 1 over root LC squared. That will give you J omega CR over 1 minus 1 over LC times LC plus J omega CR. So you can see simply now that will be 1 minus 1 will be 0, and that will simplify to J omega CR or J omega CR. So we'll have 1. Therefore when omega equals 1 over root LC, we have V naught over Vs to be 1. So at this point, which is this point, okay, corresponds to a special frequency. That frequency we call that W naught. So W naught is 1 over root LC. So at that frequency you'll have V naught equals Vs. Okay, so you can see that for low frequencies and high frequencies, for lower frequencies and high frequencies, the signal is attenuated, alright, but the mid frequencies are being allowed to pass through. Okay, we're now out the low frequency and high frequency signals and only allowing the mid frequencies to pass through. So from some omega value to some between this omega 1 and omega 2, we're allowing that frequency range to pass through, but anything below omega 1 and above omega 2, we're attenuating and filtering that out. So such a filter is called band pass filter. Band pass filter. Okay, or BPF. Now let's reconsider the same circuit, okay, But rather than now considering the voltage across the resistor, I will be interested in the voltage across this terminal. Okay, now the output voltage, so therefore in this case will be again the source voltage multiplied by the ratio of the inductor to capacitor impedance over the total impedance. Okay, so that will be j omega L plus 1 over j omega C over the total impedance, that will be R plus j omega L plus 1 over j omega C. Okay, so that can be rewritten as j, so you can multiply this out, so you'll have 1 minus omega square LC, okay, over 1 plus, so 1 minus omega square LC plus j omega RC. So that multiplied by that will be j omega RC. Okay, and that multiplied by that will be j square will give you minus 1, and omega square and LC, and that one comes from that constant there. Okay, now the same way we consider two cases. The first case is where case 1 is where we have low frequency. What we have is square values here of omega, but that will be very low. So as a result, again we'll have 1 over 1, so which is 1. For omega, very high omegas, which is case 2. Okay, so for high omegas, the squared values will dominate for high omegas. So we'll have 1 minus omega square LC over 1 minus omega square LC. So this will approximately be 1. So in both cases, when omega is a low value or at very high values, and we have output as 1. Okay, you can also analyze what will happen at the circuit here. Okay, for low value of omega, you know that the capacitor acts as an open circuit, and the inductor acts as a short circuit, but the total effect is such that it is an open circuit, and again the voltage dissipation across will be high, and all output, all source voltage will be dissipated across these terminals. And at high omegas, again the inductor acts as an open circuit, but the capacitor acts as a closed circuit. So again, the total effect is such that it is still an open circuit, and the voltage across these terminals, V0, is approximately equal to Vs. So in both cases we'll have high dissipation of voltage output to be equal to voltage source. Then if we then graph this, so for low frequency we have almost 1. Okay, and for high frequency again we still almost have. For high frequency values we'll have 1, right? So as you increase frequency, the gain then will follow such a curve, right? What's happening here is that we are now between some omega 1 and omega 2 called cutoff frequencies. So between these frequencies we are passing low frequency and high frequency, but we're filtering out whatever is in between. Okay, and such a filter is called band stop filter, or also called notch filter.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.